Now, for 1.3, we have geometric sequences and series. So we're going to be basically covering this, a little bit of sigma notation. Applications, again, this is more for IAs and longer questions. So we're basically just going to try to cover the first couple dot points, and applications will be much easier that way. Okay, so here are the equations that we need to know for geometric series and sequences. The first thing we need to notice is that there are actually 3 equations instead of 2, and there's also a concept of finite and infinite as well. And this does seem a little bit trickier than arithmetic sequences, so I'll try to spend a little bit more time on this, especially because these 2 equations look like the same thing, why are there domains, etc. And we'll cover all that eventually. But first things first, as usual, we will first define all of the variables. So within this equation, un, we already know what un is. It is the nth term, that is self-explanatory. U1, obviously, the first term. This is all very similar to arithmetic sequences. The only difference is r, we'll skip that for now, and n is obviously the nth. Okay, so r is the common ratio. So in order to understand what r is, let's have a look at what a geometric sequence would be like. This is an arithmetic sequence, 1, 2, 3, 4, etc. And it's arithmetic because it has a common difference of positive 1, right? Whereas if we have a sequence like this, 1, 2, 4, 8, etc., then if we have plus 1 here, it will be plus 2, and here will be plus 4, and that doesn't make sense because it's no longer a common difference, which means it's no longer an arithmetic sequence. However, it's still a type of sequence because we can change this common difference for a common ratio, and it would still be the same throughout. And what a common ratio is it's basically a number that you multiply, right? It's multiplication. And in this case, you multiply by 2. We'll see that if you multiply 1 by 2, you get 2. Multiply 2 by 2, you get 4. And 4 by 2, you get 8. And now we have a common multiplication, or a common ratio. So that's what r is. R is a common ratio. And obviously, we have Sn here, the sum of the first nth terms. Sum of first nth terms. And S, sum to infinity. We'll cover that later in greater detail, but first let's focus on these equations here. This is a geometric sequence because it has a common ratio of 2. If we want to find u3, assuming we don't know what u3 is, and we know what u1 is, we also know the common ratio, which is r, we can simply multiply u1 by r. If we multiply u1 by r, in this case it's 2, we'll get 2. And if we multiply by 2 again, we will get 4, which means we get to u3, because this is u1, u2, u3, right? So to get from u1 to u3, you multiply by r twice. And we know the properties of r multiplied by r. You can also rewrite that as r squared. And notice the relationship between this number here and this number is that it's 1 less. Hence, un equals u1 r n minus 1. So that's how this general equation comes to be, and that's the same thing as this one right here up there. Let's understand why there are 2 different equations, and they seem like the exact same thing, only these orders are reversed for each one. This is because for a geometric sequence, the common ratio can be greater or less than 1. In the case that it's greater than 1, it's basically just what we covered just then, something like this, where the common ratio is 2. But we can also have something like this. And in this case, the common ratio is actually a half, because you're going to be multiplying by a half every single time. And what happens is this number is less than 1, whereas this number here is greater than 1. And they are all the common ratio. So this is common ratio 1, common ratio 2. And if we were to try to find the S4 of this series right here, I would recommend using the first one. Simply because r is greater than 1. Okay? Because if we write out the equation, we will get r being 2n minus 1, or n is 4 actually, sorry, and 2 minus 1. Okay? And in this case, we will get a positive value on the denominator being 1. Whereas if we substituted r for 2, we would get -1. And that just makes it a little bit more complicated. Same with this common ratio right here. Because this is less than 1, it would be more convenient to use the second equation, because then that would allow for a positive a half. Whereas here, if you go a half minus 1, you'll get negative a half. And just makes life a little bit more complicated. But either way, both would work. Now, the reason why r cannot equal 1 is because if we want to find Sn, let's just say an arbitrary n, of a series, of a number of terms, if r is equal to 1, we'll get 1 minus 1 on the denominator, and that would be dividing by 0, which is not, we aren't able to do that mathematically. So that's why r cannot equal 1. And conceptually, if you think about it, if we have a series, let's say 3, 3, 3, this is a common ratio of 1, and that doesn't make sense because it's literally the exact same number being repeated. So if you want to find the sum of the first 4 terms, for example, here, you might as well just go 4 times 3. Right? You might as well just go 4 times 3, or 3 plus 3 plus 3 times 3. There's no need for this complicated formula anymore. Now, sum of infinity. This may seem daunting, but let's break it down step by step. Firstly, we want to go back to arithmetic sequences. Think about it this way. An arithmetic sequence, if we want to find, let's say, Sn, and n being 5, we will just have to add up the first 5 terms, and we'll get 15, right? But if I said, add up the first infinite number of terms, what would you expect? Well, obviously, if this series goes on, eventually this is going to reach infinity, because it's going to keep on increasing, right? So the sum of the first infinite terms would likely just be infinity, and that doesn't really make sense. You don't really want that as an answer, right? That's why it doesn't work for arithmetic sequences, because we assume all of the arithmetic sums are just going to be finite, okay? Because once you go infinite, even if it's a negative common difference, let's say, if it was a common difference of -1, eventually you'll reach negative infinity, and the sum of infinite terms would be negative infinity, and that doesn't make sense either. So for arithmetic sequences, it's always finite. But with geometric sequences, we introduce the idea of infinite, and that is because when the absolute value of r, the common ratio, is less than 1, say r is a half, and if we look at this sequence right here, if we multiply 8 by half, we get 4, and then so on, we'll get like very, very small numbers. And eventually, this is actually going to converge to 0. Okay, because it's going to get so small. Every single time it gets halved. Every single time it gets halved. The infinite term, the u infinite term would just be 0. Right? Because it gets so small. And this is why this actually converges towards a number. And that's the key word, convergence. For all arithmetic sequences, the sum of infinity always diverges to plus or minus infinity. But for a geometric sequence, it can either diverge or converge. And for a geometric sequence to converge, the absolute value of the common difference must be less than 1, because it must be getting closer to a value. If it was bigger than 1, then we would be multiplying eventually, and we're going to get to infinitely big as well. And that wouldn't make sense. So if we have a sequence like this one right here, which I'm showing you, if we add the first 2 terms, we get 12. First 3 terms, we get 14, 15, 15.5, 15.75, so on. And you notice the increase becomes smaller and smaller and smaller. Eventually, when we reach the infinite term, it's just going to be a discrete number. Okay, and we can find this discrete number, which is which is S infinity, by using this equation right here. So now let's do a couple practices. The first 3 terms of an infinite geometric sequence are 32, 16, and 8. We want to write down the value of r. To solve this question, we want to take an approach that is similar to what we would do for an arithmetic sequence. Arithmetic sequence, if you want to find the common difference, we just need to take the difference between 2 consecutive terms. u2 minus u1 would give our common difference. But in geometric sequences, the only difference is that we want to be dividing, okay? Because it's a common ratio. The ratio means we're going to be multiplying. So we want to be thinking about multiplication instead of addition and subtraction. So this will be the formula. Or we can use this formula right here, but this is just a quicker way to do it. And it's also a 1 mark question. And the only reason we can use this is we know this is U2 and this is U1. If we weren't given U2 and we were only given U3, for example, then we would have to use this equation. R is equal to U2 divided by U1, where U2 is 16 and U1 is 32, giving us a half. So R is a half. And we can verify this by looking at our first 3 terms. If we multiply 32 by a half, we get 16. And that happens again. If we multiply 16 by a half, we get 8, which means this common ratio must be correct. Part B, find U6. So we want to be using this equation to look for the nth term, and in this case, the 6th term. The U6, we want to find what it is. U1 is 32 multiplied by R. Our common ratio we just found is a half. And n will be 6 minus 1 because we're looking for the 6th term. Therefore, it will be 32 multiplied by 1 to the power of 5 on top of 2 to the power of 5. That's the power distributions. We distribute the powers. And here will be 32 on top of 32, giving us 1. So the 6th term will actually be 1. Now, the sum to infinity of the sequence. We want to be looking for this. Okay, this is the only equation with sum to infinity. And let's look at what data do we have. Well, do we have U1? Yes, we do. Do we have R? Yes, we do. So in this case, we actually already have everything we need. All we need to do is just substitute it in. Okay, so sum to infinity, it will be equal to U1 being 32, 1 minus a half being 32 on a half. Now, dividing by a fraction is the same as multiplying by its reciprocal, so we get s to infinity is 64. Okay, and that's the discrete value. So if we were to add up every single term in this geometric sequence, it would be 64, meaning it converges towards 64. And the reason it converges, again, is because R is less than 1. The absolute value of R is less than 1. Right, next question. The first term of an infinite geometric sequence is 4. The sum of the infinite sequence is 200. So this we've already been given is s infinity, and the first term, so U1. So this is the information that we're given, and now we are asked to find the common ratio. Now, if we are given s infinity and we are given U1, we can simply use this equation to find R, because this is the only unknown. So if we just substitute R into this equation, let's have a look. 200 equals U1, which is 4 on 1 minus R, and we can solve for R to be 0.98. Part B, we want to find the sum of the first 8 terms. Therefore, we are looking straight at this formula, sum of the first n terms, and we'll make that 8. Therefore, we substitute into this equation. Now, which one do we use? Well, for simplicity, since R is less than 1, we want to be using this one, because we'll end up with a positive value after we do 1 minus 0.98. So Sn being S8 will give us U1 being 4, 1 minus R 0.98 to the power of 8 on top of 1 minus 0.98. And I'm pretty sure this is a paper 2 question, so you can just put that into your GDC or any other calculator that you have, and you'll end up with 29.8. Alright, so for part C, find the least value of n which Sn is greater than 163. So for this type of question, what we want to do is I like to set Sn to be equal to 163 first. Okay, because in these type of questions, this number doesn't actually need to be one of the terms in the question, and we'll find out more about that later. If we set Sn to be equal to 163 and we use, let's say, this equation right here, because R is less than 1, we will get Sn, which is 163, is equal to U1 being 4, 1 minus R is 0.98, to the power of n on top of 1 minus 0.98. And if we use our calculator or GDC and solve, etc., and we solve for n, we'll find that n doesn't actually show up to become a whole number. It will be 83.5. And that's pretty weird, isn't it? But if we think about it on a simpler example, let's say we're given this geometric sequence, and we are asked for when s of n is greater than 13. Okay, so in this case, s of 2 will be 8 plus 4, giving us 12, and s of 3 would be 14. And if we did the same method that we did for this question, we'll find that n would be a value between 2 and 3. But we know that n has to be a whole number because we can't have a half term, so we will choose n to become 3. We will round it up. Why do we round it up? Well, because if we could think about it conceptually, if it was s2, it would be 12. So if we round it up, 14 would be greater than 13. But why can't we do n equals 4? Well, if we do n equals 4, then s of 4, which is the sum of the first 4 terms, it will be 8 plus 4 plus 2 plus 1, which will give us 15. That's still greater than 13, isn't it? Well, then we have to remember, back in the question, it asks for the least value of n, which means 3 would be still the most suitable. So going back to this concept right here, if we want to find the least value of n, which is greater than this, we must be rounding up, okay? Because any number, if we chose n to be 83, then s of n would be slightly less than 163. Okay, so s of 83 would be less. Whereas with s to 84, that would be greater than 163. And we know this because in between this step, we got s of 83.5, which doesn't actually exist, is actually equal to 163. Okay, so the 83.5th term is equal to 163. Therefore, anything less would result in it being less than 163, and any number more, any integer more for n would be greater, right? And obviously negative numbers can come into play, but in this case, since our common ratio is a positive number, that means the sum of the first n terms will always be positive, and it will be increasing for every single value that n increases. Okay, now for the sigma notation for geometric series, and basically this is just the same thing. I copied this format of this. So this is what a geometric sequence would look like for the nth term. And if we want to expand this as we did for the arithmetic sequences, we can substitute n equals 1 first. So we get the sum of 3 times 2 to the power of 1 minus 1 plus 3 times 2 to the power of 2 minus 1 plus 3 times 2 to the power of 3 minus 1. And this is basically a geometric sequence. Why? Because if we expand all of this, we'll find that our first term would be 3 times 2 to the power of 0. Any number to the power of 0 is 1, so we get 3. Here we'll have 3 times 2, which is 6. And here we'll have 3 times 2 times 2, giving us 12. Okay? And we find that this is a geometric sequence of common ratio 2. And we can identify this r straight away just by looking at the sigma notation of this number, which is under the power of n minus 1. Okay? And also our u1 would just be this 3. So it's very similar to this. I'm sure there are probably harder examples out there, but this is just the basics for sigma notation in terms of geometric series.